Okay, so we are going on. Okay, so now we are looking at the types of ultrasound, okay, of Doppler ultrasound. And so there's continuous wave Doppler, there's pulse wave, there's color, and there's power Doppler. Yes. Now, the key thing about the continuous wave Doppler is that at this mode, two of the crystals or two different crystals will be operating when you are using continuous wave. What will happen is that the one group of crystals will be sending out the ultrasound waves into the body, and then another set of crystals will be receiving these waves coming back from the body. Okay, so one will constantly be sending, one will constantly be receiving. So the advantage of continuous wave Doppler is that it's able to give us a better, a more accurate, amount of the velocity of any flow without aliasing. Aliasing is something we describe in, or we use in ultrasound scan to describe a phenomenon that happens when you are not having enough sampling. Usually that occurs in the A and the B mode of scanning. Remember, we said that A mode is largely used for measuring distances, okay, and as well as B. And M can give you some motion, okay, but there are it's not accurate when it comes to actual measurement of the velocity. That is why we use the continuous wave Doppler for that, okay. And the limitations for which we can't use those other modes for measuring velocity as accurately because of phenomenon we call aliasing. So this that's without that. The only disadvantage, however, is that it will sample everything along its path. Okay, so sometimes it's difficult to isolate specifically a structure that you might want to calculate. So then the pulsed wave. So as the name suggests, it gives short bursts of sound. Okay, so it doesn't just condense. Sound doesn't continue through. It comes in pulses. Okay, and it uses the same crystals to send and receive the signal, unlike the continuous wave that some crystals are sending, some are receiving. But with the pulse wave, because it is doing so intermittently, when it gives out a burst, it will wait for it to receive the same crystals will receive the reflected sound waves before they give out again. Okay, all right. And usually when we are doing 2D images, that is when we use this technique. Okay, so it can sample at a specific site along the Doppler line. So this one, you can carefully isolate out various structures that you might want to measure or sample out. Okay. The disadvantage, however, is that the maximum velocity which can be displayed is limited. The signal will always alias at a given point based on the transducer frequency. Yeah, sorry about that. My power just went out. Okay, so where were we? I think we were at, yeah, so we're at the pause. Okay, so color Doppler, I presume. Okay, so for color Dopplers, the main thing I want you to understand is that it gives us color imaging for flow. So typically, you would see, when they are doing Doppler, you'd see arterial blood as, it will demonstrate arterial blood as red, and then it will show venous blood as blue, okay? And also based on, it uses their speed of flow and their rate of flow and all that to calculate that. So that's the main thing about color Doppler. So it's basically used to assess the flow, velocity, and direction. Okay. Yeah. Okay. Yeah. So basically, it uses a computer to convert the measurement into an array of colors. What else? What else? Yeah. So basically that. Okay, so I've written here, color Doppler displays blood flow towards the transducer as red and blood flow away from the transducer blue. This color visualization combined with a standard ultrasound picture of a blood vessel shows the speed and direction of blood flow through the vessel. So it's basically for speed and direction of flow through the vessel. And most basically, it will show arterial blood as red and venous blood as blue. Thank you. Now, power Doppler. So power Dopplers are more, roughly said to be 5 times more sensitive in detecting blood flow than the ordinary color Doppler. And it can get those images that are impossible with the color Doppler. So where the color Doppler is limited, that is where the power Doppler comes in. And is used to evaluate blood flow through vessels within solid organs. So for instance, if you would use the ordinary Doppler, for instance, if you are suspecting a DVT, you know. However, if you have maybe a mass that you are suspecting to be malignant, if a malignancy, you'd want to know whether there are, how the blood flow is in the organ to be able to plan how you go about it at surgery. Or sometimes you go and open up and realize actually the blood vessels on the thing, if you try, you spend the rest of the time in theater and the patient is likely not to come out. So power Doppler, because it's more sensitive, is able to go deeper through solid tumors to tease out their blood flow. So yeah, so that's about, so those are basically the principles and the types of various ultrasounds that we've looked at. Now we want to look at some of the terminology that are used in describing ultrasounds. And as I've said, ultrasounds always come with reports. They always come with reports. So some of this information is good for you to have a fair idea or fair understanding of some of the terminology that are used in there so that you better appreciate what they mean. And then also when maybe you get a chance to start using your hands on ultrasound, you can also know the types of terminology to use. Okay, so we'll go through a few of them. Right. So the first one to look at what we call acoustic shadowing. Acoustic shadowing. Acoustic, I'm sure you all know that acoustic has to do with sound, okay, or hearing. And shadowing, of course, you all know shadowing. So it's characterized by a signal void behind structures that strongly absorb or reflect ultrasound waves. So it's just like when you stand in front of, for instance, you are standing between the sun and something, you realize that the shadow will fall so that the light from the sun will not touch that thing. So for instance, the ground, and you see what will result in a shadow in that state. That is the same thing that happens when the ultrasound waves go through the body and they hit the structures. As I said, some of them can be reflected, some can be deflected, and so on. When they hit a structure, and that structure greatly absorbs or reflects all the sound, then you realize that the behind it or behind that solid structure or that organ, the place, there will be no echoes coming from that side. There will be no echoes coming in from that side. I have a few pictures that we'll look at to get the picture. All right. So the echoes, basically when the ultrasound waves pass through the body, I think the second term should have come before the second. Let me do it to make it easier to understand. Okay. All right. So echo. So the basically when the sound waves hit any structure, some of it is reflected back and perceived by the transducer. So what the transducer perceives are what we refer to as echoes. Just like how bats move around, they produce a sound, and based on the echoes that they get, they're able to tell what structure is ahead of them and are able to avoid colliding into structures ahead of them. So it's not the same thing. The reflection of the ultrasound waves back to the transducer from a structure, what we refer to as echoes. Acoustic shadowing are what I've just explained, that if the structure or the organ that the waves hit, if they absorb all of it or reflect all of it, then behind that means that no sound waves will pass through it. And so the space behind it will look blank or look dark. Okay. Now, echogenicity. Hold on. Okay, so so the echogenicity refers to the capacity of a structure in the path of an ultrasound beam to reflect back sound waves. Okay, so echogenicity, so we would say that it is highly echogenic or it is not very echogenic. That means that when you say it's of a high echogenicity, that it means that it's able to reflect more sound waves back. Okay, and someone or a structure with lesser echogenicity is one that will be able to reflect lesser sound waves back to the transducer. All right. And so you can comfortably say that a highly echogenic organ or structure is more likely to have greater acoustic shadowing as compared to a structure with a lesser echogenicity. Okay. So qualifying them, when we say hyperechogenic, it means that the structure is able to produce more echoes or greater echoes. Okay, and hypo, of course, is just the opposite of hyperechogenic. All right, then anechoic. So anechoic simply refers to an area on the ultrasound that is not getting any echoes back to the transducer at all. We'll see how that also looks like on the picture. Now, when we say it is of complex echogenicity, that means that it has echogenic and anechoic areas. So it has areas that are reflecting a lot of the sound waves and areas that are not reflecting sound waves. So it's not uniform. Okay, it's complex. Okay. And the echogenic simply has to do with solid structures. Okay, and their echogenicity is the ability to reflect as much back. I think I need to rearrange these things here. Good. So the other term we would see a lot is when you hear the terms homogeneous, heterogeneous, homogeneous and heterogeneous. So homogeneous, simply, homogeneous is an English word. So when you get a structure that has uniform, the picture looks very uniform. There aren't hyperechogenic and hypoechogenic areas. Then you say that it is homogeneous. Okay, like the liver. If you see a picture of the liver, for instance, you realize that it is homogeneous along all of its body. And when it is heterogeneous, then you see that the echogenicity or the darkness or the whiteness that we are talking about is not uniform across the whole structure. All right. Now, hyperechoic. a relative, this is a relative term that refers to, I think I've explained this already, hyperechoic and hypoechoic. So hyperechoic simply means that it is reflecting a lot more sound, or it is very echogenic, whereas hypoechoic means that it is not very echogenic, and so it is reflecting less. Much of the sound waves to be able to pass through. Then also is acoustic enhancement. It's also known as positive enhancement. So this refers to increased echoes deep to structures that transmit sound exceptionally well, like fluid-filled structures. So some of the structures that are able to reflect sound well, you see a phenomenon behind them that we call acoustic enhancement. So we'll look at a few pictures of some of these. All right. Now, so this on my left, hey, the time is going already, right? The time goes fast, fast. Okay, so this is the lever on my left here. You can see that this picture here is very homogeneous because the density of the white here is fairly uniform. I hope you can all see that. This is how the lever would appear like. Okay. So when we are talking about echogenicity, it's the same black and white, but the nature of the appearance of the picture is what helps us to know whether this is genital. So this lever we are showing here, we say that it is echogenic. Okay, it is echogenic. Okay, homogeneous echogenicity. So this is homogeneous. So we can ask you, what would be the typical description of the lever on an ultrasound report? Then you want to mention things like it is what? Echogenic, it is homogeneous, and all of that. I mean, homogeneous echogenicity. Now, if you look at the picture on the right, so this one, obviously, you can see that it is not uniform. There are areas of whiteness interspersed with areas of blackness. Okay, so the darker parts are places that are hypoechoic or hypoechogenic, whereas the white parts are hyper-echogenic. Okay, so this is not uniform. So we say this is heterogeneous. For instance, if you have maybe incomplete abortion or retained products of conception, this is how you might see the interest. See this heterogeneous picture here. Okay. Now, this picture on the bottom left is also simply to help you understand what we mean by hyperechoic and hypoechoic. So you can see we have the normal and abnormal shown here. So basically, hyperechoic structure is one that is more, I mean, it's appearing more gray or more white than the visual surrounding structure. Look at the one on the bottom right here. You see that the image in the middle here, the well circumscribed image here, is not as white as the surrounding structures. Okay. So this is hypoechogenic. So all of these places are echogenic, but the inside here is hypoechoic or hypoechogenic. Right. You have some more? Yes. Now, the top left. Can you see the top left here? This is how anechoic looks like. So there are no, there's no feedback at all. There's nothing here at all that reflects any sound waves. So it is completely black. How we can all see. So anechoic means that anechoic. Hypoechoic, you'll see some darkness, but you wouldn't see the you see here, even though it's hypo, you still see some white inside. That means that there are certain things inside this structure that are still reflecting some sound. Unlike here, there is nothing at all. So this is anechoic. On the top right, you can see white, you can see the white, very white parts of this organ here, the parts that are not so white. So the very white parts are hyperechoic. They are hyperechoic compared to the surrounding structure. So we use these things relative, I mean relation to others. Now, let's look at the one on the bottom left. I'm sure you can all see that this is a place that is almost anechoic, okay? Now, usually when you see anechoic areas on ultrasound, they are likely to be fluid or fluid-containing structures, okay? Now, let's look at acoustic enhancement. This is the phenomenon where we said that when the sound waves pass through an area which is anechoic, when it gets to the other wall, so the waves are coming, the sound waves are coming from up here like that. Then when they get here, they're able to pass freely through this anechoic area. So when they hit here, more of them are able to pass through here freely. So more of them hit here. And you can see that right behind the wall of this cyst here, there's hyperechogenicity here. Okay? And this is what we call acoustic enhancement. Acoustic enhancement. Because the sound waves are able to pass through a place that is anechoic, when they hit the other wall, the sound waves are enhanced. They are enhanced. That is what referred to by as acoustic enhancement. Okay, so you see an area of higher reflection happening after an anechoic area. So I can put this, put lines in there. An area of increased echogenicity or increased reflection of sound waves following an anechoic region is likely, and this describes a term called, you all know that it's acoustic enhancement. Now, aside acoustic enhancement, we also have what we call acoustic shadowing. Acoustic shadowing. Now, we are going to explain acoustic shadowing, and you tell the difference between that